of correlations. We'll take the van der Waals equation as an example. Suppose I have take this. This may be not a part of the syllabus, but it's something I'll refer you to the standard textbooks to learn more about it. I just want to mention it. So I have, let's say, introduced new variables, namely the reduced pressure. So the reduced pressures are related to the actual pressure, but are scaled by the physical quantities. Right? So I introduce these. And then substitute this into this. So wherever I have P, I will substitute PC times PR. Wherever I have P, I will substitute PC times PR, and so on. Right? So when I do that, and then I get PC also will come into the equation, and log of AB is also there. So suppose I substitute further PC equal to PB and PC equal to A by 27B squared and PC is equal to 8A by whatever. I mean, I don't exactly remember, but probably these are correct. Whatever it is, if written expressly, I substitute that also. Then I get a striking relation in terms of the reduced pressure, volume and temperature. That equation can be written like this. More important than the form of the particular form which derives from the van der Waals, the more important thing to know is that whereas if I have P equal to express the function of volume and temperature, then I get the parameters A and B. But if I have PR in terms of PR and here there are no parameters at all. What this really means is it implies a well-known principle of known as the corresponding states principle, and the corresponding states looks like this because this is now applicable for all van der Waals equation states. Whatever may be the values of A and B for a particular van der Waals fluid, and I take another van der Waals fluid, it will have a different A. However, the equation in terms of the reduced pressure, temperature and volume will be the same for both the two van der Waals fluids. Let's now consider two states of two different fluids. Suppose let's say I consider T1, D1 and T1 to be state of fluid 1. We are talking only about van der Waals fluids, and a different state of fluid 2. So it's now another fluid, another state. So I assume that I'm going to write P2, B2 and T2. We'll assume that P1 is not equal to P2, B1 is not equal to B2, T1 is not equal to P2. However, suppose B1, B2 and T1, B2 are such BR1 is equal to BR2. I can easily choose two states of the two fluids such that the specific volumes are different, the reduced volumes, because the critical constant of the two fluids will be different. So I choose in such a way that the reduced volume and the reduced temperature are the same for the two states of the two different fluids. Suppose I do that. So it's possible to choose. What this really means is that V1 by Vc1 is equal to V2 by Vc2. So it means I can easily choose. Suppose we say V1 is the specific volume of fluid 1. I can always choose, since I know the critical volumes of the two fluids, let's say, then I can choose V2 so that it is given by this relation. Suppose I choose corresponding states means there's some correspondence between two states, right? And that's what I'm trying to explain. Similarly here, and so what this equation implies is that then, if this is true, and both behave like van der Waals fluid, so both of them, let's say the van der Waals fluid is a very good model, then we get that PR1 is equal to PR2. So there is a correspondence between the two states of two different fluids. These are two different states, but there is a correspondence between them to the reduced quantities. In that, the reduced volume and reduced temperature are the same for the two states. The reduced pressure will also be the same. It's quite obvious from those equations. This is basically the principle of corresponding states. Now, what this really means, why this was attracted in earlier times, was that it sort of gives a universal equation that if I express the equation of state in terms of reduced quantities, I don't need any parameters at all. So we can have one universal relation between PR, VR and PR for all fluids. So I just have one equation, one plot, let's say PR versus PR for various PRs. And with that, I can determine the PVD properties of all fluids. But clearly that will not work out, and it has not worked out. Mainly because, as we have seen, the van der Waals model itself is not because this is inferred from the van der Waals fluid, and we know the van der Waals fluid is not an accurate representation of quantitative representation of the properties of the fluid. So the question then is, let us say that suppose we introduce another parameter. Not all fluids will follow a universal correlation, but we introduce one additional parameter, right? And let's call it alpha, which will depend from substance to substance. And then for all fluids with a particular value of alpha, will have a universal correlation relating PR, VR and PR. This is the history of the corresponding states type of correlation. But what was later on found was, instead of relating P, V and T, let's relate Z, right? And then Pitzer introduced, this is how he introduced the eccentric factor. What he said was, for fluids with a particular eccentric factor, right, I can have one universal, it's a limited universality. For those class of fluids, I can have a correlation between the compressibility factor and volume interval, and I'll show some correlations taken from the standard sources. Here is one, very easy to understand. We can switch off the lights. Now, switch off all the lights. Then you switch off those lights. So now you can see what is plotted on the y-axis is Z. You might not be able to see it, but where we take it from E, that is that now you can probably see it. The compressibility factor is plotted. So this is basically representing this, although the parameter here is not omega, but actually the parameter is not anything, so let's not worry about it. So you can see that what is plotted is Z versus PR. I'll plot it first. So various values of PR, it's actually representing only the supercritical region. Right? So TR, this is TR equal to 1 and this is TR equal to whatever. So you can see so the point made here is that you can see that the solid line is the average curve based on the data for hydrocarbons. So the point made here is that many of the hydrocarbons might fall fairly close, but some of the other substances are falling slightly away. You can clearly see that there is many of the points are falling outside the curve also. So this is simply without any parameter. You just plot that BR, TR, obtain the experimental data for hydrocarbons and get the curve, and then try to plot for various substances which include some other substances like nitrogen, carbon dioxide and water, which are not hydrocarbons. And you can see some of those are falling outside. So it's not what it is saying is that there is no universal correlation. You cannot simply get the data for hydrocarbons and expect all of them will fall on the same plot. So an attempt was made to introduce another parameter and see if for a fixed acentric factor whether there is a universal correlation or not. Right? Now this is giving the entire information, not just the supercritical. It's a bit more difficult to understand. You can see that you have the liquid, vapor, envelope and so on. Right? And then also the supercritical region. This is probably from Sandler, reproduced from one of the older books. So I am not going to discuss this. This of course has a ZC of 0.27. So this is obtained from for a fixed value of ZC rather than omega. Right? So I am not going to discuss any more. What I want you, this is more of a historical significance. Because earlier, since the other questions, the limited introduction and given, this is not very relevant anymore. This is more of a historical curiosity. Because nobody really uses these correlations. You have equations of state which have n number of parameters. So these were useful when computing facilities were very limited and plots were more in use. So we wanted to compress a whole lot of information in one plot. So this is what led to this, and I have not really covered the full detail what all was done. But now it is not very relevant because you have equations of state are all complicated once, and Aspen Plus and many of the softwares will have a choice of different equations of state, and there are more and more attempts to improve the equations of state, to add more parameters or change the form of the V dependence or the T dependence so as to make them reproduce or predict the experimental data more accurately. And so that is the way in which the whole field has progressed, not in terms of compressibility factor correlation, but in terms of actual equations of state with more and more parameters and better equations of state. So we don't have the time to go into all the latest developments, but this is more from a historical viewpoint, and it illustrates the corresponding states principle, which is really looking for a universal correlation between various properties. But many corresponding states correlations have been proposed for diffusion coefficient, viscosity, and so on, where the scaling parameters are in terms of characteristic energies and characteristic distance, molecular distance, and so on. So this is one instance of the corresponding states which is implied by the van der Waals. So other than that, I don't really have anything more to say. Are there any questions? If not, we'll move on to the next chapter, which is mixture. Maybe switch on the lights. As we did for the pure components, the mixtures, we will first cover the theory and then look into applications. Right? So the theory, if you see, everywhere there is the development will follow exactly along the lines of the pure component. Only the complication will come because of additional variables that you have to deal with. It's more of a extra effort in terms of manipulations and so on, but in terms of principle there will be nothing new that will be added. Okay, so we started with this for a pure component. Now for a mixture, we are going to consider a mixture which has C components. And we also first consider the homogeneous states of a mixture. So that means only one phase. So for that, I will argue that the specific internal energy, apart from being determined by the specific entropy and the specific volume, as it was for pure component, in turn, C minus 1 composition variables would have to be taken into account. So composition variables, this represents the mole fraction of component 1. And we know that there are C components. Now this can be regarded as a local fundamental equation because it can be easily extended to handle non-homogeneous states also, even though we consider primarily only homogeneous states. Right? So this will be the local mole fraction, as you have seen in for example, diffusion. We easily talk about concentrations or mole fractions varying with position. So we can talk about local mole fraction because the homogeneous state mole fraction is defined as n1 by n, right? Where n1 is the number of moles of the component and n is the total number of moles. For non-homogeneous states, it's a locally defined variable. There is no question of capital N1 by n, but it's a local mole fraction. So we can talk about local mole fraction also, but we soon specialize to homogeneous states. So these are C minus 1 in number. So these are the, because we know that all mole fractions have to add up to 1. They don't local or global for a homogeneous state. Right? So what this means is sum of A equal to 1 to C, set J equal to 1. So I'm deliberately chosen Z rather than X or Y because often X is used for liquids and Y is used for mole fraction of vapor. Right? So it might give you the impression that this is restricted only to liquids or gases. It doesn't refer to any particular phase. Right? It only talks about the mole fraction of a homogeneous state is what we consider first. So this is what it is, and the general equation. Now I have to, the variation in the internal energy is not only on account of the entropy and the volume, but also on account of the mole fraction. So I will assume that the variation with respect to entropy and volume, the coefficient, the differential coefficient will continue to be given by the temperature and pressure of the mixture, just as we had for the pure component. But here I will introduce quantities which may be called as the generalized chemical potential. So mu J star is a generalized, so they will be related to the chemical potential that we will normally associate it with. Now this portion is very rarely covered in this manner, except in some very obscure old sources. You have to pay attention to what I am doing. You will not find this readily available in the standard textbooks. So now we immediately specialize to a homogeneous state. Of a mixture. So that is the total internal energy is simply given by the total number of moles multiplied by the specific. So until here, we can apply even to non-homogeneous states, as is often done. When treating non-equilibrium, then it is conventional to assume a local equilibrium approximation. And in that, relation which is valid for systems in equilibrium continues to hold for non-equilibrium or non-homogeneous states also. We won't get into that. We will be dealing with the first homogeneous state. So here, so we now see that the total internal energy is determined by n rather c plus 1 variables. If you see, the total internal energy was for the pure component was determined by 3 variables, S, P and N. Here it is determined by C plus 1. So, rather C plus 2. Right? We have C plus 1 here plus N. C plus 2 variables. When you put C equal to 1, you get 3 for the pure component. However, we want to write this not in terms of S, P, multifractions and N, but rather in terms of the capital S, that is the total entropy, the total volume, and the total mole numbers. So here we show that this is possible because after all, right, S is for the homogeneous state, S is S over N. The small v, specific volume is capital V over N. Clearly, the total internal energy can be expressed in terms of the total entropy, the total volume, and the total mole numbers. In the same way, now N here, you have to clearly understand is sum over J equal to 1 to C Nj. Because we want to bring in the dependence on each individual mole number that is hidden here also. On top of it, it's hidden in each one of these variables. So after all, what is S? It is again S over N. So N is no longer the variable there, the total mole number, but rather we have to consider the individual mole numbers. So similarly, and this clearly is N1 by N, and this would be Nc minus 1 by N. You can see all the mole numbers come into play. And on top of it, you have the total entropy, total volume. You can very easily see the next development. We will now look at what is dE by ds. Clearly show that this is equal to dE by ds, E, and dE by dV is, I will leave you to prove that. There is nothing new that's going to come out of this. What will make this whole development more complicated is when we get to the chemical potential, just as we did here. Right? So here also we prove that dE by ds is. And then when we did dE by dN, we introduced this as the chemical potential, and we did a whole set of manipulations which proved that the chemical potential is actually equal to E plus PV minus ds, which was earlier already defined as G. Right? So we will now come to that shortly. So now we want to ask, now there is not just one mole number, but there are C mole numbers. So we now introduce first the actual chemical potential quantity, which is called as a chemical potential, not the generalized chemical potential, but the actual chemical potential mu I, which I now define as, which is really dE by dNi, meaning ST is under standard notation. And all the mole numbers other than I are kept fixed in this differentiation. This is now referred to as the chemical potential of component I. This is how we are introducing, just as we introduced for the pure component. Now what is this, how is this related to the various other quantities? We will now see that. Right? So first, I will have to look at it through this. So I already know what I want to do is to relate it to P and the mu A stars. That's what I want to do. Right? So I can first write this as you have E. So it's a product of two terms. Right? So I want to differentiate with respect to Ni. So the easiest is to first write it as E times d by dni of n. What is that? Is equal to what? This is actually E times dn by dni. What is dn by dni? Huh? 1, right? Because n is n1 plus n2 plus n3. So when I differentiate with respect to particular ni, keeping all other whole numbers fixed, that means in the sum, I'll pick only ni. And when I differentiate it with respect to ni, I'll get 1. Right? So that is very clear. But now, what is more complicated is how to differentiate this. So clearly this is n times. So wherever it is convenient, I will put capital N. You have to understand it's a sum over all the mole numbers. But some cases I have to bring out the mole numbers explicitly, because you might think what is dn by dni, right? So you should know what n is, right? So wherever there is bound to be confusion, I will write it explicitly. So now I will have to write this as dE by ds. Procedure is identical, right, to what we did for the pure component. If you go back, you will see procedures are the same. Times ds by dni plus use of the chain rule. There we would have had ds by dn, dv by dn, and that's how we had for the pure form. Now we have to also deal with it. This is what we have. So clearly this is already known to be t. This is minus p, and this is mu a star. So those we know. All I have to do is to calculate ds by dni, dv by dni, and dzj by dni. First two are going to be quite easy because I have s is equal to s over n, and here instead of differentiating with respect to ni, I have to write this as s over sum over j equal to 1 to c and j. Now tell me what is ds by dni. So clearly this partial derivative means the same. S, B, and j not equal to I are kept fixed. That's what it means. This is not writing it each and every time. That's the transformation that I meant to ask. Right? S anyway is not dependent on B, but it's dependent on S, the capital S, and all the C mole numbers. So tell me what this is. Minus, yes, minus, I will differentiate, S is a constant, 1 over n, I will first treat it as a variable and write it as S times minus 1 over n squared, and then dn by dni, that is there. This is clearly equal to 1. So this is simply minus s over n squared. The same way can be shown to be minus p over n square. There is very similar to what we had for the pure compound. The complication now comes for, it is important to remember that I have to consider only C minus 1 of the mole fractions. Right? So let's now take an arbitrary mole fraction, Zj. Where j can be from 1 to C minus 1 and calculate what is dZj by d in I.